And then what about the view, Ed? Do I hit X? No.
Actually, just click that, see if it covers it up and brings up the slides. Oh, it didn't. Yeah, perfect.
Is that good?
Yeah, that's exactly what I needed.
We good?
It's recording.
Okay. We probably should get started, Tim.
Um,
Okay. All right, everyone, let's get started. I'm Ed Fitzgerald, the president of Emeritus Center, and I thank everybody for coming out today. In fact, this is a great turnout. We had to go get extra chairs. It's almost standing room only. Happy to have with us our speaker today, distinguished Professor Emeritus Tim Lance, who's also a member of our board, actually. So it's like having one of our own here. And of course, Dean Napkin, our co-chair for programs. I'll turn it over to Dean, who can do the formal introductions of Tim, and then we'll get started.
Okay, thanks. Good to see everybody. Now, sit tight because I promised him as much time as he wanted to talk on these topics, several topics. So it could be 6 tonight. We get to send in if you like, whatever.
we'll start the order now,
Yeah.
Vince.
So it's my pleasure. It's Tim Lance, Distinguished Service Professor Emeritus at the University of Albany. And he was on the math faculty for more than 30 years, almost half that time as the math chair. For several years, he serves as the campus's CIO when he joined the board of the not-for-profit corporation NYSERNet, which provides the research network in New York. In 1998, with the university's blessing, he took on the additional role of president and chair of NYSERNet, a dual role he carried for 8 years until he retired as full-time faculty in 2006. Pardon me. Tim continued to run NYSERNet for another decade, guided throughout in both roles by the results of his own research and that of others. Last spring, the Emeritus Board made Tim an Emeritus Fellow, and traditionally, awardees give a talk on some aspect of their work since retirement. Tim will do that now. Tim, it's all yours. Excuse me.
Thank you, and thank you all for coming. This talk, stuff got added as I was building this talk because I realized partly it was in Dean's introduction, was that being a member of the faculty is a wonderful platform to do other stuff. Aside from what you're going to get judged on, you're going to get judged on your service and your teaching and your research. At least that's the way it was when I was. I think teaching's gotten a little bit more important, but other things outside of the traditional university duties. And so I'm going to include various people who stepped out of their traditional role and took on other roles to our great benefit. The first one I want to mention is Ed Stone. He is just retired. The top picture of him is roughly the time when Ann and I met him, when the Keck Foundation wanted me to come out there as their science officer. Ed had various science projects in his life. His first official science projects were the 2 Voyager spacecrafts and a model of the Voyagers at Wright. Both Voyager 1 and Voyager 2 are outside the heliosphere, so they're truly in interstellar space. Voyager 1 may be dying. It's got erratic transmissions and some sign of internal trouble. Voyager 2 had gone quiet, but just this past August, we sent an urgent "Are you there?" message to Voyager 2, and 13 hours later got a reply saying, "Yep, I am," and started sending reliable data. He was having siesta or something in interstellar space. Dr. Stone was already a chaired professor at Caltech, and he took on this role of first the Voyagers and then running JPL for about a decade and a half. And so he's a maybe 2 decades example of somebody that stepped out of his comfort zone, and we all benefited from the direction he took. By the way, told Anna me that he started in a 2-year school. That was all they could afford. And luckily, the people there recognized the jewel that they had and passed it along for the rest of us. This, in a way, is part 2 of the talk I gave in April 2022 about NISANET. This one, in lots of ways, was easier because it was all history. Most of the history I lived, and some of it I helped shape. But it was worth mentioning at least the key points in it. What are some of the things we did? We, New Yorkers, all of us in New York, shared the risk and the expense. The question was, were we going to be controlled by New York State, which had given us a grant to get us started, partially get us started, or by us? And the head of the Science and Tech Foundation said this will only work if NISANET's, and the government said it will only work if the government controls it completely. And the head of Science and Tech said, no, it'll only work if the government stays out of it entirely, and they won. So we worked with carriers. Ivan Seidenberg, we first handed off this project because we were using telephone lines to the Bell system, but New York Telephone at the time. Ivan Seidenberg, who later became the CEO of Verizon, said we learned TCP/IP from NISANET. And actually, we learned it together. In 1987, we created the world's first ISP. Testifying before Congress, we think the internet has financial possibilities. That sounds ridiculous now, but that was a radical idea. And we began the second Manhattan Project, the first one being creation of the atomic bomb. So this was building out fiber in Manhattan and global exchange point in New York City. What was important for me is that what wasn't in that talk that I had is the first 6 or 7 years that I was running NISANET, we were dealing with the effects of a catastrophic choice the board had made for the first president. I was the board chair at the time, fired him 5 months later and became both the chair and president. And then he began one legal challenge after another. He had come out of OSTP, the Office of Science and Technology Policy in the White House, and had helped build the Welcome to the White House website. And he used his friends to make that a multi-year, multi-million-dollar cost to us. I was driven always by the research, and I think that was a good position to do, because some of the things that we wanted to do were going to push us to build networks that were beyond what we thought was within reach. The first one was the Large Hadron Collider, huge facility in Europe. It was looking for Higgs boson and succeeded, and won a Nobel Prize for finding Higgs boson. Within New York State, we had the relativistic heavy ion collider, and it's a lot like the Large Hadron Collider that perhaps have been left in the dryer too long. It's a neat place to visit. You can actually drive inside. You get these warning signs that this is a zone where there are high energy beams, and when you come out, you may be a mutant. And I don't have any proof to the contrary of that. Throughout my entire time heading NISANET, there was a fierce debate about what's the next big science projects. In terms of satellites, the James Webb Space Telescope is sending back breathtaking information that we couldn't have gotten any other way. A lot of it's in infrared zone because we want to look back billions and millions of years. But that was a debate about what was going to happen and what wasn't going to happen. In terms of things like the Large Hadron Collider, the United States decided the electron ion collider would be the next project to peek further inside of the atom. And then Brookhaven was chosen for that site. And there's a gives a schematic, and if you go to that website, it will actually show you how they accelerate, how it's going to work. It's going to be using the RHIC, the relativistic heavy ion collider, but upgrading it. LIGO, another one of the huge projects that is a schematic of what two black holes look like. And this is the LIGO team in New York that sort of led the computational problems working on the so-called Einstein equations. They're called Einstein equations, but Einstein and David Hilbert, Niels Bohr, a lot of others contributed to the evolution of them. And in that bottom picture is the team at Syracuse, and Duncan Brown, who's the leader of it, is on the far left. And the top is the one of the two initial LIGO light interferometer gravitational wave observatory. Those arms are perpendicular, 4 kilometers long. They shoot a light beam in, split it goes out, comes back. And when a gravitational wave passed through it the first time, it stretched one and compressed the other by about the diameter of a proton. But it was fine enough that they could detect it and say, yes, this is what the Einstein equations said that we were looking for. I think a huge factor in a lot of these science decisions was Jack Marburger. He was a physicist by training. He was the president of Stony Brook. He then became the director of Brookhaven National Labs. Kind of pushed into it. They were having the graphite reactor at Brookhaven was leaking, and there was a great deal of problems about what's the danger to the community. The danger was actually quite low, but he was so open and honest and listening to people. And if they had a question, coming back with an actual answer, not something that's glossed over answer. He's dead now, but he was critical he was President Bush's science advisor, and some of his colleagues criticism, why are you working for President Bush? He doesn't care about science. And his feeling was, well, it may be uncomfortable, but if the president is going to make decisions about science, and I'd rather have him get a correct answer than an answer that's not correct. And he served him for 8 years. John Holdren, who was President Obama's science advisor, said of him, he was an esteemed scientist and public servant. Those of us who had the privilege to know him benefited greatly from his extensive knowledge, pragmatic thinking, and warm friendship. And we take comfort in knowing that his determination to explore new scientific frontiers and his enduring commitment to America's far-sighted focus on science and technology will be continued by all those he inspired. So President Bush approved the funding, multi-billion-dollar funding for some of these projects that we've seen, and Jack Marburger was behind that. There are other efforts, the Human Genome Project, one by Celera Genomics, and the initial one, which was NIH funded, to basically map the 3 billion base pairs in the human chromosome. There's, I won't blow it up just because of time, but that link gives you a sort of an expansion of what happened in the 10-year time frame of the Human Genome Project. And it was pretty spectacular to see what happened. I think that one of the critical things happened around 1980, 1990, 91, right around, I'm sorry, right around 2000, maybe 2001, when they were first announced the joint results. Celera Genomics decided they had mapped out a certain part of the human genome and they were going to patent it. And Bill Clinton and the British Prime Minister, Tony Blair, made a joint statement saying, no, the human genome was going to remain forever in the public domain. Now, did they have the authority to do that? Lots of times we ask questions about presidential authority, but they had the moral authority to do it. This was the right thing to do. The genome belongs to everybody. Now, the particular tissue that was worked on in the Human Genome Project came from an individual, we have no idea who it is, from Buffalo. I don't know if it was a Bills fan or not, and whether or not the genome has been profoundly affected by that. But these two people came up with one of the things, the fact that the genome was now completely in the public domain, people could explore and develop tools. And these two women developed the CRISPR-Cas9 gene editing tool. They won the Nobel Prize in 2012. Broad Institute in Cambridge, Mass. Based on their work, did something, they did it for prokaryotes, they did something for prokaryotes and eukaryotes. It was really a routine exercise because I figured it out myself and I'm not a biologist. And they applied for expedited patent review and they had a patent before they ever considered the one from these two. I think that this changed. The European Union has granted all patent rights to CRISPR-Cas9 to Dr. Carpentier and Gemma Doudna, and the U.S. is slowly rolling back what they granted to the Broad Institute. But this is not like the human genome; it's a tool. So it's more legitimate to say this is something that I'm actually going to try to patent. All right. Prologue for this talk. I know that what drew everyone here was nuclear fusion. And it's talk about quarks and gluons. The person on the left is Jerry Friedman. I met him first in 92, something like that. He did joint work with Richard Taylor and Henry Kendall, and they were using the Stanford Linear Accelerator. It's this beautiful facility. It actually crosses the San Andreas Fault, and the big one hasn't happened yet. So physics will change a little bit when the L in Stanford Linear Accelerator is no longer L, it's more like broken line accelerator. And I don't have any pictures from the collisions that they were looking at. But the picture on the right is a collision it's a quark gluon plasma made at the RHIC, the Relativistic Heavy Ion Collider at Brookhaven National Labs. And somehow out of that, we've got to tease some meaningful sense, which is part of what we're going to be doing in this. And looking for what are the mostly geometric things that's going to use geometry to pull out the meaning behind what looks like noise. What they discovered is that protons and neutrons are actually made up of smaller particles. And for the moment, those are now not divisible. And protons made up of 2 up quarks with a 2/3 charge and one down quark with a negative 1/3 charge, and a neutron, which is made of two down quarks and an up quark, so it's got a charge of 0. But the things that you're pulling together, these quarks, they're all charged. So there's a tremendous amount of energy that's required to pull them together into a proton or a neutron. And roughly 80% of the mass of protons and neutrons, the mass of it comes from the energy required to hold it together. It's sort of fascinating that the gluons are most of it. Their work won the Nobel Prize in 1991. So I met him, I guess the year after he won the Nobel Prize. He's the coolest guy. You could just talk to him. He's really a neat guy. All right, we'll talk a little bit about AI. Let me just start with the I. Oxford English Dictionary gives this definition: ability to acquire and apply knowledge with skills or the collection of information of military or political value. And in some sense, this sort of predates the AI stuff, because this is a definition about humans, by and large. So our attempts to define AI, we've got probably the first formal one was by Alan Turing in 1950. And his schematic was, you've got person A and person B in person B and C in computer A, and the person C is communicating with the computer or with a person, and it passed the Alan Turing test for machine intelligence if the questioner can't tell it's talking to a machine or to a computer. I think probably the best, we've got some choices, possibilities for computer A. One is Watson. I think this is probably our best AI machine that we've made thus far, and it's conversationally extraordinary. We'll get to who the two people are, because it could change quite a bit in what we're doing. I thought you guys see the Jeopardy challenge where they totally whooped the two contenders. Largely because Jeopardy is a challenge for something that's easy for a computer and hard for people, accumulating lots of facts and spew it out without necessarily knowing anything. I thought that Watson's most interesting answer in the Jeopardy challenge was his answer to what is Toronto. It was, and people wondered, and I don't even remember what the question is, but it was what American city and then other stuff. And they said, how could they not know that Toronto wasn't in America? There's a link there if you want to see a very cogent analysis of what's going on. Both the head of IBM research at the time, John Kelly, and the project director, David Ferrucci, told me that it took them some time to cede control for Watson's learning to Watson. After that point, they could be less sure what Watson was thinking. Had money been no object and there'd been many Watsons, they would have argued with each other and would have come up with the fact that, well, Toronto was not an American city. Duh, that comes first. But it doesn't have that meter on it. Wonderful at collecting facts. So, who are the possibilities for the people? Well, William Shakespeare is one of them. What if the person that this poor person communicating with a computer or some other unknown person that person happens to be William Shakespeare. And I sent you all got an email with a description of Cleopatra by Plutarch and by Shakespeare. Now, you look through it, Shakespeare borrowed wholesale from Plutarch, but he breathed life into it. I think in the now, I guess they're still voting on it, but the ended writers and actors strikes in Hollywood. They were worried about, what about AI, and is it going to replace us? And so you can ask the question, well, was Shakespeare imitating Plutarch when he wrote that description of Cleopatra? I don't think so. I think he was breathing life into it. Emily Dickinson, she was her first half of her 30s was during the Civil War. And she understood probably keenly the suffering that the soldiers and the families on both sides were going through with all the suffering. The other day, we had to put down a much loved cat from cancer. And Anne found this poem by Emily Dickinson, Bustle in the House. The bustle in the house, the morning after death, is solemnest of industries enacted upon earth. The sweeping of the heart and putting love away, we shall not want to use again until eternity. How did she capture that? Does that sound like Chat GPT? I don't think so. Now, this is a hard bar. Both Shakespeare and Emily Dickinson are a pretty hard bar for Chat GPT. But early on, I thought that, we ought to have a Macbeth test. You ought to be able to create a play of the power of Macbeth, but a new one. And one of my colleagues in this, Greg Bell, who was working at Lawrence Livermore National Lab, was head of the Energy Science Research Network, but he had his PhD in Berkeley from Shakespeare. And he said, I can't pass that test. So let's get something a little bit easier than the Macbeth test, but we'll give you some others that give you a sense of how close we are to AI. First, let's look at Fermat's last theorem. This is the theorem that says the expression x to the n plus y to the n equals z to the n doesn't have any solutions for n bigger than 2. And Fermat said, I found a wonderful proof of this, that the margins of this book aren't big enough to contain it. And I think I know what his proof was. He attached to the circle 1 over p away around the circle, and then took all the multiples of that, and then all the integral combinations of those, and you get this wonderful ring called the cyclotomic ring at p. And then you use unique factorization. Factorization of 28 is 2 times 2 times 7, and that's it, other than reordering, or a 1 or minus 1 in the front. You use unique factorization, and it falls out. And I think the world believed that. And then they started to think, well, it's not quite so obvious, but we still truly believe that cyclotomic rings have unique factorization. It took 2 centuries for Ernst Kummer to show that no, it didn't have unique factorization. And so we can't use that Fermat's idea for proof of the Fermat's last theorem. Andrew Wiles presented a proof in 1993. It was corrected in 1995, and then over 6 years, a full proof of the modularity theorem was shown. If they have pictures here, if it's current, I was not around, despite what you may think, at Fermat's time, so that was just a picture for Fermat. But this is a picture of Andrew Wiles about the time that he announced his theorem. He was at Princeton when he announced it, and there was a problem found in the most interesting part is not the 95, the 93 to 99, the 6 years for the full modularity theorem, because that was going to happen. It was the first 2 years, because it was wrong. And now you've announced this most famous, one of the two most famous problems in the world. And he had basically given up. He tried all sorts of things and it didn't work. He thought the problem was with something called the Grobner maze. And he said, I'll take one last look at the Grobner basis. I'd at least like to know why I failed. I don't understand what went wrong with the Grobner basis. And in the process of doing that, he realized the failure was actually the direction of the proof. It was in looking at that failure and had this aha moment. Reminds me a little bit of the discovery of penicillin, where you're realizing these spoiled cultures are not the problem, they're the solution. So these are people trying very hard, and it took us from Fermat's time till 1995 to actually have a proof of Fermat's last theorem. So that's how hard it is for people. How durable is the human brain? This is a picture of Bobby Kennedy shortly after he'd been shot during a presidential campaign. One of the last things that he did was Roosevelt Greer, the football player, was there, and he was the one that wrestled the gun away from Sirhan, or other people were shot, but there would have been much more harm done if he hadn't done that. But one of the last things Bobby Kennedy did was Rosie Greer was kneeling over him and he was saying the Hail Mary. Very high function in a brain that's been blown apart. It's just astonishing. Mention also people whose brains were being attacked. John Nash, and if you've seen A Beautiful Mind, it's about John Nash. He was a topologist, basically. I never saw him talking to imaginary people. Ann and I both met him. His wife was more beautiful than Jennifer Connelly, who played him in the movie. And he was just very shy. If you said hi to him, he'd nod, and he'd write on the boards. And sometimes it was nonsense, and sometimes it was stuff that was brilliant, in which case I didn't understand it. Also, another famous mathematician, Dan Quillen, died of Alzheimer's, and he used to work at home and write in these notebooks. And after his death, his wife published all of his notebooks, and they're in PDF forms. If you look for Dan Quillen's notebook, you'll get it. And toward the end, you could see much like John Nash, his minds were places where it was gone, and places where he was right on target, still being the brilliant John Nash. Closer to home, June 14th, 1980, I'm an epileptic, have been all my life, but I didn't know it, didn't recognize the partial complex seizures. And my first total seizure was at the top of a ladder, and I fell to the drive, and I broke right side of my body. And I was working, it will open, on a paper at the time. The person on the right is Peter May, who was a big influence on me at the time. But I was working on I'm getting to that. I was hoping, well, don't forget, I came out a mutant after going inside of the rig, so that explains a lot. But I was working on this paper, Steenrod and Dyer-Lashoff operations on BU, and it's thinking seemed like such a tremendous problem. When I fell, I sort of broke the right side of my body. All that was good because that absorbed kinetic energy before my brain hit. my skull hit, and then the shock wave across the brain, when it scattered on this side, I lost 40 to 50% of the brain on the left side of my body. And I know that because I saw the CAT scans. And thinking seemed like such a tremendous difficulty. And so I find this mouse really hard to, where is he? There it is. Get rid of that. I asked Peter May if he saw a difference. I asked Anne if she could see difference, and she said no, but she took a vow not to notice. But Peter May said no. Also, but I felt it, and I used to tell the students that. I had some that had really terrible traumas that were in auto accidents, and they were in comas for a long time. And they all said the same thing about 6 to 9 months, where thinking was a tremendous difficulty. I don't know if something happened then, or you just stopped checking. I don't know. When it's inside your head, you can't tell. But that lasting 6 to 9 months seems to be universal. Another example of ability, we're trying to find out, human beings struggle with really hard problems, but I think they're problems that both in writing and in the physics and the mathematics, machines can't get them. Not yet, maybe not ever. But in 1696, Johann Bernoulli posed this problem, this least time curve, and I don't like the little thing that goes along the vertical and horizontal. But the question is that if you've got a little bead, what's the shape of a wire so that if a current slides along that bead, driven only by gravity, that it gets to the other end in the least amount of time? And a number of people submitted solutions. When Bernoulli was a great mathematician, he had 2 sons, both great mathematicians, saw this one anonymous solution. He said, this must be the work of Isaac Newton, claiming I know the lion by his paw. So my friend, Greg Bell at Lawrence Livermore said, all right, let's put it to GPT-4. We're not asking it to solve the perchristochrome because it's got access to the internet. It'll say, oh, I found it on the internet, dummy. We're saying, how could you decide that it was Newton just based on the elegance of the solution? So he gives a long answer, and lots of stuff he has to say, right? It reminds me a lot, my view of as a teacher, when a student puts down that many things that don't exactly answer the question, they actually don't have any clue what they're talking about, so they're trying to snow me with that. Bernoulli had a 35-watt computer between his ears, and GPT-4 was a multi-megawatt computer, maybe multi-gigawatt, I don't even know. GPT-4 had full access to the internet. So why didn't it think to look up the other solutions from that time, which I did? And I think Newton's really does stand out. It's incredibly elegant. But would it have recognized if it's elegant? I don't know. This is not a hard problem. Not a hard problem for human beings. It's beyond GPT-4. We want to apply this to physical problems. And my first example, and it's particularly topological solutions that we want to apply to physical problems. Claude Shannon, he was the sometimes call him the father of communication. He wrote a paper on, I'll pull it up, working for the Bell Company, Mathematical Theory of Communication. And it was a fundamental shift. Before Shannon, circuits were absolute things. And after Shannon, he said, circuits are noisy. and we've got to distinguish the signal from the noise. It was a fundamental change that brought about by Claude Shannon. We had things like error correcting codes and things like that, but you had to have that idea. And in this paper, his methods are topological. He's using topological methods to say where to see the real message inside of a noisy channel. A lot of this is about physics or mathematics. And I personally don't think that mathematicians and physicists are very different, but there's an example that you can do. What Einstein would call a Gedanken experiment. You've got a room and they've got a fire in one corner and a fire extinguisher in the other corner. And you let a physicist walk in the room and you'll see the fire, see the extinguisher, grab it, squirt it out, put it out. The mathematician will walk in, see the fire, see the extinguisher, think to himself, a solution exists, and walk back out of the room. So here we have Jupiter, one of my favorite places. It's on my bucket list. I know it's inconvenient to get to. It's governed by the Navier-Stokes differential equations, and no solution. We have no known solution for them. We'll come back to Navier-Stokes again. This was one of my classmates, Charlie Pfefferman, who solved some wonderful problems in Fourier analysis, but he wrote this beautiful paper that highly recommend to you if you want to learn about Navier-Stokes. The one-dimensional part of it is just familiar F equals ma, and it gets worse as it gets larger. And for Jupiter, it's pretty complicated. But I'm saying a solution exists. Remember I mentioned before the Steenrod algebra. I was doing that paper and I was trying to do something with the Steenrod algebra. This person, John Milner, this picture, not concurrent of the paper. He was, he's in his 90s now. But he wrote this paper, oops, I'm gonna go, in the 1958, or it appeared in 1958. Here you are. Take a look. I'm used to having the mouse pointer. This paper, the Steenrod algebra and its tool. The Steenrod algebra was something that everyone was trying to understand because it was very important for homotopy theory, for a lot of problems in topology. And everyone understood, it's an infinite dimensional algebra. Everyone understood that it was incredibly hard. If you get it up to dimension 15, going to 16 is going to be much, much more difficult. It was far beyond worse than not being NP complete. And then in 1957, it was published in 58, John Milner said, well, let's take a look at the Steenrod algebra. And notice that we can create this little thing, giving it a coproduct, which makes it a Hopf algebra. Now it's got a product and a coproduct that gives it a tremendous amount of geometric rigidity. And then once you see that, you take the dual where the structure just falls out, or the structure falls out if you're John Milner. But the question is, how did he see that? This is a good example of how Salieri must have felt. Where did Mozart get that? But that was 1957 that he submitted it. 1958 was the proof. More astounding things. by John Milner. I think he's one of the world's greatest mathematicians. He gave a series of lectures at Cornell in 1965, not long after he got the Fields Medal for his finding exotic spheres. I said before, Charlie Pfefferman solved some famous known problems in Fourier analysis. John Milner asked questions nobody thought to ask, and then he answered them. So his stuff is astounding. The first link is for the lectures he gave at Cornell, and it's kind of neat to watch because there was no PowerPoint. He was just using pen, but there are 3 of them all together, and they're so relaxed and so understandable. It's like you almost thought of it yourself and laid back. That hides the fact that this is a tour de force of revolutionary discoveries in topology over the previous decade and a half, most fundamental ones due to Milner himself. So highly recommend that. And then, when I first started at Nisenet, I was asked to do a paper on differentiable structures on manifolds in this paper. 2 things about this. First, a great deal of this is sort of privileged to walk in the footsteps of people. Notice that the first theorem is due to Milner. This is his discovery of exotic spheres. It's a remarkably simple one. The other thing is that writing this, Anne edits all my stuff. Martha knows about Anne's editing. And she's looking at the first draft and stared at the page for a while and puts her finger halfway down the page and said, the paper starts here. She didn't know any of the mathematics, but she could tell that up to that point I was writing for me. And after that point, I was writing for the audience that I'm trying to reach. So that's where it started and where she put her finger down. And that is simply the power of language. Now I ask you, we'll go back to GPT-4. Who was it? Dan, you had the thing that could spot language from one of these machines. Would you send me the link? Yeah. Could they look and realize the paper starts here? I don't think so. Anyway, this is a picture of me around 2002, but it has the Milner braid over my shoulder. So I thought that was the only honorable way to have a picture that's as closest to I can come to when I wrote it. And I want to give you a couple of examples, and then we will wrap up of how we use. Oh, by the way, in that paper, I learned years later that John Milner was the referee, and he made no corrections, and he said, there are a couple of things in there about links to number theory that I didn't know. Now that had to be a lie just to make me feel better about myself, because I'm not sure there's anything he didn't know, but that's what he said. Linear regression. If you guys are familiar with this, you've got a scatter plot, and there are nice formulas for this. This goes through the line where the X and Y coordinates are the averages of the X values and the averages of the Y values. Not a surprise. The more surprising thing is the slope of this line. It's the correlation coefficient times the standard deviation in the Y direction over the standard deviation in the X direction. See, lots of people nodding, you know that. And the 2 standard deviations, that's not a surprise, because if the one is wild and the other is not, it's going to bump it one way, and if the other's wild, first it's not, it's going to push it down the other way, but it's some measure of the wideness. But the correlation coefficient, that's the amazing part. If you take all of these points and you take all their X values and put them in one long, 100 tuple, and take all the Y values, put them in one long tuple, the correlation coefficient is the cosine of the angle made by those two vectors. It's an astonishing piece of geometry. I was teaching an elementary course in stat when I realized it, and just staring at the board for a while, and they thought, well, I don't know what they thought. I finally told them what was going on. Gauss had to know this, but it was probably too elementary to let us know, so we had to rediscover it on our own. Another example is splines. If you have a set of points, and we'll talk about the one on the left, and you're trying to figure out the trajectory of something. This happened in the early days of radar. What's the path if we've only got a couple of select points? And if you've got a spring wire that you can feed through that and then let it go, so it springs back to its natural state, it's gonna Hooke's law. And what it tells you is that the acceleration second derivative is constant on each one of these segments. So this thing is differentiable, but its second derivative exists, but the third derivative doesn't. It's going to be a polygonal line connected together. This is a natural manifold that's related to trying to find a trajectory. And in the case of trying to track an aircraft, it's probably the right one, because the aircraft is going to follow something where you're not having spikes in acceleration. You're just going to be as smooth as possible. So here's an example where you've got a manifold where there's a fairly direct reason why this would work for a lot of physical situations where the spline is the right way to anticipate it. We go back to climate, or Jupiter, start with Jupiter. We don't have any complete solution for Navier-Stokes, but there are features in this, like the red spot on the left. We can say a great deal about what's happening near there and about its durability. And with more data, we can have more durability. Even some of the areas that look turbulent are actually stably turbulent. It will take a long time for that to dissipate. So we know some stuff, and we can do it topologically. I said that, Jupiter was on my bucket list. The other one you might as well know is Glacial Lake Missoula. Problem in this one, it's easy to get to, but it's 12,000 years ago. It was formed in Montana, the Ice Age, when this valley was dammed up at one end, and you had a ice dam that was 2,000 feet deep. It was greater than the volume. It was about a quarter of the volume of Lake Michigan, or Erie and Ontario, bigger than Erie and Ontario combined. And when it broke, it all fled to the Pacific in a hurry. So part of my bucket list is to be on a surfboard there on the surface of Glacial Lake Missoula when the ice dam broke. But the same things that we try to figure out with the what's going on in Jupiter, we can try with weather. It's really important with weather. The stability that we can get predicting this upper right is Hurricane Sandy. We're getting better, and we've got things like finite element method that we can use. Do a quick trip through fusion. I promise you fusion. How do we make helium? Well, simplest way is to have deuterium, that's the D, so it's 1 proton, 1 neutron, and tritium, 1 proton and 2 neutrons, and you collide them together at tremendous energy. They don't want to go together. They're charged, right? And you're trying to push these things together. And once they get to within 1/10,000,000th of a meter of each other, then the strong force takes over and pulls them in and does the work to fuse them. And energy is released in the process of doing that. and the helium loses some of its mass, about 5% of its freestanding weight of the particles separately. Remember the quarks? We talked about the quarks. There it was, the amount that would be released is 160 times as much energy as happens in a hydrogen bomb. So we really don't want to have a quark bomb, Q bomb, as they had on the Mouse That Roared movie. The hydrogen bomb, we figured out this is the one way that we know how to make helium. I don't know how many globe incinerating events it will take to fill one child's helium balloon. So it'd be better to conserve helium and find other buoyant things. But Edward Teller is often called the father of the H-bomb, but person that broke had the critical insight was Stanley Ulam, the geometric topologist. And John von Neumann did a lot of the groundwork for it. And we have a Turing Prize. It's the Nobel in computer science. But the architecture that we refer to as the von Neumann architecture. We have a lot of the standard architecture that we know is due to that. Oppenheimer was a brilliant physicist. He gave up a career as a physicist. If he just stayed a physicist, he would have won the Nobel Prize while he was working on the Manhattan Project. That's when we got to the point that we could actually verify some of the things that he'd already written down. This is going to happen. In the bomb, cast a cloud over Oppenheimer and over all of us. But only Edward Teller testified that Oppenheimer should be stripped of his security clearance because of I don't know. I think jealousy. He was not a very nice person. How do we make fusion other than bombs? Tokamaks, this one way, tori. And on the left, you see we had a breakthrough at the Joint European Torus. We're all funding that, released 59 megajoules energy. And this is kind of a stylized picture because the left-hand side shows the start of the fusion plasma forming inside that donut. And I don't want to run the movie, but recommend looking at that link because it's a cool movie and seeing it in how quick and chaotic it is inside the torus. We had a breakthrough in the UK at a spherical torus. There are several of them. One's at Princeton. First time ever that we achieved sustained temperatures at this. So the contenders for nuclear fusion, controlled nuclear fusion for the moment, are either ITER, pictured on the left, gigantic thing, or the spherical tokamaks on the right, the Princeton one on top and the UK tokamak on the left. And you can see people in those drawings. They're much, much smaller. It's a huge facility. ITER actually has paid a tribute to all of you as a maritime. They've realized recently that it's been losing data and they don't know why or how, and how they could possibly reconstruct it from what happened. And so they're frantically trying to rehire people who retired from the ITER project because they're the ones that actually know how it works. So any of you worked on that project, they need you over there to figure out ITER. And finally, the National Ignition Facility will be very quick. This is experimental, but this is the first time we got more out of a nuclear reaction than we put in. There are lasers off to the side. It doesn't count the energy required to power the lasers, but the amount of laser energy that went in was 2.5 megajoules, and the amount of laser energy that came out from fusion. So they there's either a BB-sized capsule, spherical capsule goal, and inside that was a much smaller diamond capsule, and inside of that was deuterium and tritium, and that was blasted with all of these lasers and hundreds of lasers, and we got more energy out than we put into it. They repeated it again the following year, and it was stronger outcome. They want to take it up an order of magnitude, but don't forget, even though this thing is like the tip of a pin, I mean, it's a stick of dynamite. So they got to put concrete around to try to continue it. And my last comment is just stay out of your comfort zone. This is a paper I did a number of years ago with John Kelly, who's then the head of IBM Research, and Ed Reinfurt, who ran NISTAR, which was the funding agency for science and technology in New York. And we talked about the Large Hadron Collider as a sociology experiment. But writing the paper was a sociology experiment itself. Could the three of us, Ed with his perspective from the state, John Kelly with one of corporate IBM and also not being able to say everything that he knew, and my much freer one as an academic, get together and come to terms on this? We did, but Ann knows it was a bumpy ride. And so we have to stay out of our comfort zone, and I've gone long, but I thank you.
Either comments, either speak loudly or you'll have to use mic. Anyone?
A friend of mine just asked ChatGPT to create a painting that combines Salvador Dali, some other Bosch character, and it came up with an incredibly spectacular painting. Do you see any in the arts? You're talking about sciencey stuff and theorems and forks, and what about in the arts? Do you think ChatGPT can come up with a song as pretty as classics?
No, I don't.
Yeah, I've seen impressive.
It's
stuff.
impressive looking. Those two quotes that I gave you, Plutarch's and Shakespeare's description of Cleopatra. I'm on a advisory council for the regents, and I talked about it with them, and I said, here's an example of, the difference between Shakespeare and Plutarch. And one of the people on this council said, I don't see a difference. So, we vary quite a bit. And I couldn't look at that and say, this sort of my question, who's person B and person C, who's looking at it and say, oh, this looks like a computer threw together. I know that my co-conspirator in the Junior Science and Humanities Symposium asked ChatGPT where to find judges for it. And the answer was, go to the places that usually provide the best judges. Well, thank you. You might see if Hunter Biden wants to buy that art from you. Right? And I'm not doubting that. I'm saying I'm not the one to say that. And he didn't create the two sides of it. He took two things and blended them. So, different problem.
Anyone else?
Yeah, since
Did your brain injury explain why you were Chad for 15 years?
yes. Actually, I heard the discussion about that. They said, he's very bad with brain damage, not much good as a mathematician. What can we give him that doesn't require anything? Well, the chair. So, and I won't realize that, God, I got stuck here. Yes.
Patience. Most interesting examples was the gentleman, I forget his name, who not only devised solutions, but he devised the problems in advance. Is ChatGPT capable of that?
No. John Milner, and he's such a humble person too. You say this is what a spectacular paper. He'll say, you really mean that? And that could be sarcastic, you clown, I'm John Milner, and you making a comment, but it's not, it's sincere. When I was in grad school, we had a Magnificat moment. Anne was pregnant with Peter, and Peter was a wild child in the womb. He never stopped kicking, never. But she'd come in to pick me up at Fine Hall, the math building's library, and it was a sunny day, and Peter was quiet for once. And she thought, I'll just sit here and enjoy the sunshine and Peter being quiet. And Milner walked into the library and he immediately started kicking. So what did he sense? I've got a lot of things that are the example that I gave of his finding the structure of the Steenrod algebra. You wonder, the exotic spheres is much more subtle and unexpected. But just that one, it was already there in front of us. Why didn't the rest of us see that this thing was a Hopf algebra and had this rigid structure that, a great deal of the ideas are either his or inspired by things that he did, and they realized that, oh, with that I can do this. So being around him and watching him was and there are a lot of wonderful other people that I got to see, but he was special.
Anyone else?
Thank you, Tim. Really appreciate
Thank
it.
you. Went long. Not too bad.
I told you, you had all the time that you needed.
Yeah, I know. But people
You can just pull it
pick up
right
their
up.
kids.
Huh?
They have to pick up their kids and
No, no, this was fun, believe me. So let's end this.